Okay, well, good morning or good afternoon or whenever it is that you're watching this. As I mentioned in class, I have, or I am recording now, a lesson for you to watch tonight, Thursday night. I'm not going to be here tomorrow. I've got to be down in Houston for the day, so I'd like you to watch this. Thursday night, come in and work on an assignment with the substitute, Mr. Davey. Can't remember his last name. Anyway, I will see you Monday, so have a good weekend. But in the meantime, we will continue talking here about 4.7, inverse trig functions. Okay, I know that we began this section already, and so I don't want to rehash everything that we said before, but I do want to summarize. I want to summarize it. So remember, the most important thing about an inverse trig function Okay, this will be our little symbol for inverse trig function. Is that it takes in a ratio value, all right, and it gives you back an angle value. So this is our trig ratio. And this is our theta, okay? In fact, let's change that y, if you are not opposed to it, to a theta, and that's a good statement for you to recognize, all right, to kind of have put in your head. So remember that the inverse trig function and the original trig function are inverses of each other. That means they undo each other. And that would make sense since if I took the original trig function of both sides, implication arrow, right, trig of theta equals trig of trig inverse of x. All right, what happens here? Well, the trig function, right, and the trig inverse function, they're inverses, all right? So composition here, remember composition of inverses, they cancel, okay? And you just get back the x. So that's real common for us. We recognize that the trig ratio of some angle is equal to some ratio value, okay? So that's a real brief summary of what we talked about on Tuesday. But let's get more specific about that. So remember that the inverse sine function okay, let's review the graph of that guy. All right, so it takes in ratio values and spits back out angle values, but remember, the angle values that the inverse trig function spits back out, they're prescribed, okay? Meaning they can only be from a certain interval from the original sine function. In this case, inverse sine can only spit out angles between negative pi over 2 and pi over 2, okay? And so the graph of this guy looks like this. okay, inverse sine. So, again, remember domain. Here, let's go like this. Domain, -1 to 1, range, -π/2 to π/2. And remember, there was a picture that I wanted you to associate inverse sine with in your mind, and it's this picture here. That inverse sine can only give you back angles between -π/2 and π/2. Okay? Only in there can inverse sine give you back angles. That's very important to remember. All right, cosine, oh, not sine, again, cosine. Oh, also remember, let me say one more thing. Remember that the other way to write the inverse trig functions is to use the little prefix arc. So we could write this as arc sine. They mean the same thing. Or arc cosine. And the graph, recall, so again, when the math community got together, they decided that the best angles, the most practical set of angles to send the cosine ratios back to are the angles between 0 and pi. We talked a little bit about why that is. Probably the biggest reason is so that you can solve triangle problems like you encounter in physics and in geometry. It's very helpful. It's very natural, very intuitive to send these ratio values here from -1 to 1 to these particular angle values. So the graph of this guy looks like the following. Okay, you can kind of see cosine there. If you were to turn this around, if you were to turn it around, you can kind of see it. Okay, technically you'd have to flip it outside the plane, but you can sort of see it if you did this. This is not the proper way to rotate it, but it'll just help you to see it a little bit. See it there? You can kind of see kind of cosine. See how you see the cosine arc there, the blue arc. Anyway, okay. So this is arc cosine. And what do we want to know about that? Well, the domain of this guy, same thing as arc sine, -1 to 1. But the range of angles that arc cosine spits back out is from 0 to pi. Okay? Now, that range produces or gives us this picture that I want you to think about when you think about arc cosine. All right, you've got to remember that arc cosine can only give back angles here between 0 and pi. All right, the kids last year called this windshield wipers. So you can imagine going back and forth here like a windshield wiper. Okay, so arc cosine is windshield wipers. All right, arc tan . Well, again, the math community has to decide on a certain slice of tangent to use for its inverse tan function. Remember, functions that are not naturally one-to-one don't have inverse functions. They would end up sending their input values back to an infinite number, or at least more than one output value, which makes it a non-function. So you need to take a slice of tangent so that the outputs are only produced one single time. All right, and that way you would have a one-to-one function, and you can create an inverse. Well, the most natural slice to take is that, if you remember when we graphed tangent, we talked about that first cycle. That's the most natural slice or cycle to use for the inverse tan. So inverse tan function then corresponds to this guy. Consequently, is this guy. This would be what, pi over 4, right? This would be negative pi over 4. Okay, inverse tan, all right, or arctan. You can see tangent in here. If you were to flip it, out of the plane along a diagonal axis of symmetry, you would get the tan function back. Okay, so what are some of the features of inverse tan? Well, the domain for inverse tan is simply the range of tan, right, which is all reals. The range of inverse tan is negative pi over 2 to pi over 2, very similar to sine, except it doesn't include those endpoints, right? So we use parentheses. So negative pi over 2, not including the endpoints, pi over 2, parentheses. Right? And then the picture that I want you to associate with inverse tan is this one. Same picture essentially as that for sine, inverse sine. Only real difference, and it really doesn't show up in the picture, is that inverse tan can never give you back pi over 2 or negative pi over 2, right? Why? Well, because tangent doesn't operate on them. So they could never be produced by inverse tan. So there's a sense in which you have a hole there, or it doesn't actually make it to those values. You don't have to put those little circles in. I just wanted to point that out, okay? Now, out of everything I've just said here for the last 15, 20 minutes, these last 3 pictures here are probably the most important. You have to know where or what set of angles these inverse trig functions are allowed or permitted to give you back or to spit out, okay? That's the most important thing to remember here. So let's look at some exercises. You're going to have an assignment this weekend. I know you don't have a book, but it's on. This is page 347. And I'm going to do, you're going to do exercises from 5 to 48, not all those, but that's the set of exercises you're going to be working in. I'm going to do some examples from these, and so it should be enough to help you through the homework, all right? So let's look at number 9. Let's start with number 9. Let's start with number 5. Okay, so for exercises 5 through 20, Dr. Larson simply wants you to evaluate these inverse trig expressions, okay? Now remember, the number one most important thing about an inverse trig expression or function is that it gives you back a theta, all right, an angle. So you're looking for an angle here. Well, knowing what you know about inverse functions, what is this angle that I'm looking for? It's the angle whose sine ratio is 1/2. Okay, if I took the sine of both sides of this original little equation I created here, I'd have 1/2 equals sine theta. So I'm looking for the angle whose sine ratio is 1/2. Using the picture model that I used yesterday, the idea is this. So for the last 4 sections, we've been working with the trig functions, right? So we've been taking a trig function, in this case sine, and we've been taking, angle values, right? Some theta value, and we've been getting a sine theta out. Okay. Well, now we're taking, and this, remember, this sine theta, this is some ratio value. This equals some ratio value. In this case, equals a half, right? So now we want to do the inverse of that. We want to take the inverse sine, okay, arc sine or sine inverse. He used arc here, Dr. Larson, so I'll just keep it like that, arc sine. Not sure if you would write the E there on the end of it or not, for the word. Anyway, arc sine. And we want to know where to send the half to, okay? Well, again, there's all kinds of angles, there's all kinds of thetas that we could send it to. But remember that arc sine is only permitted, it's only permitted to pick an angle, or to send a ratio back to an angle between negative pi over 2 and pi over 2. So the first thing you might want to do, now look, some of you are already getting down the bow ties in your head. You probably know the answer to this without even having to draw this picture. But in case some of you are still struggling with that, the first thing we would want to ask is, where is the trig ratio positive for sine? Where's the trig ratio positive? Well, that would be here in the first quadrant, right? Quad 1. And more specifically now, where is the trig ratio equal to 1/2, 1 over 2? Well, since sine is opposite over hypotenuse, then that's the guy we're looking for right there, right? Between 0 and pi over 2. Well, you guys know what that is. That is pi over 6. So that is our answer. Theta is equal to pi over 6. Okay. All right. I won't draw the pictures for all these. It's going to put you to sleep, I know. All right. How about let's do 9 and 11. All right. Number 9, arctan of radical 3 over 3. Okay, again, we're evaluating this, which means we're looking for what? A theta, right? Remember, all inverse trig values are thetas. They're angles. You're looking for an angle. You're looking for the angle whose tan ratio, if I took the tan of both sides of this little equation I just created, I would have this expressed, this statement, this equation. You're looking for the theta whose tan ratio is radical 3 over 3. Okay? You don't have to write all this stuff all the time. I just want to make sure you can think about this backwards, because that's what we're doing. We're working backwards here, right? Well, radical 3 over 3, that's the same as 1 over radical 3. So let's think about that. Well, first thing I would do is, again, recognize where arctan is permitted to give you back angles. Arctan is only permitted to give back angles there, right? Between negative pi over 2 and pi over 2. Well, of these two quadrants, this angle has to be in the first quadrant. Why? Well, because the ratio is positive, right? This is a positive ratio. Okay, positive there. So again, you're going to draw or think about, you don't have to draw a picture, but you can think about a terminal ray landing in this first quadrant that gives you a tan ratio of 1 over radical 3. Well, what would that be? Now, again, tan is what? Tan is opposite, right? Y over adjacent, or y over x. So if this is a 1 over radical 3 angle ratio angle whose tan ratio we're looking for this angle, this guy right here, whose tan ratio is 1 over radical 3. Well, you should know that one. That's one of our nice angles, right? Which again, just like the guy we just did, is pi over 6. So theta here equals pi over 6. Okay, so we're just working backwards, but we're working backwards to a prescribed set of angles. All right, we don't have our just free choice of angles here. Okay, I mean, I realize that there is an infinite number of angles that give you a tan ratio of 1 over radical 3, right? An infinite number, just an infinite number of coterminal angles with pi over 6. It could be just add 2 pi to this. That's 12/6, right? So this could be 13/6 pi. It's a nasty 3. 13/6 or 25/6 or yada yada, right? But we're not allowed to get these angles. We're only allowed angles between 0 and pi over 2. So these guys we can't even consider. This is our guy, okay? Pi over 6. Okay, so remember, the most important thing to know about an inverse trig function is what? That it spits back an angle, a theta. You're looking for thetas when you evaluate inverse trig functions. The second most important thing to know is where you're allowed to look for these angles. Okay? All right. How about 11 and 17 and 19? How about this guy, 11? Cosine inverse of negative radical 3 over 2. So, again, I won't draw a ton of pictures here. We'll kind of start weaning ourselves away from the pictures. But what I'm looking for is an angle over here between pi over 2 and pi, right, that has that cosine ratio. Now, how do I know it's between pi over 2 and pi? Well, because this cosine ratio is negative, right? And so between the first and second quadrants, remember, this is the only interval you're allowed to look for your angles in for inverse cosine. Since the ratio is negative, the only place to get negative cosine ratios is in this second quadrant. So my ratio is radical 3 to 2, which means I want my long leg to be on the horizontal here, and the hypotenuse is 2. Well, again, by this point, you need to be able to recognize that as a reference angle of 30. This is a reference angle of 30, which means that theta that I'm looking for right there is what? What is it? 5/6 pi. That's right. I heard it out there. 5/6 pi. Okay? All right. How about 17 and 19? Sine inverse of negative radical 3 over 2. Okay, similar to 11, a little different though. It's the inverse sign, right? So for this guy, I am thinking what? I'm thinking of an angle between negative pi over 2 and pi over 2 that gives me that ratio, gives me that sine ratio of radical 3 over 2, negative radical 3 over 2. Well, first thing that should jump out at you is that negative sign. The only place to get a negative sign ratio is between these two quadrants, 4 and 1 is down here in 4. Okay, so I'm going to try to draw it rather proportionately. I want the long leg, the y side, right, to be radical 3, in this case negative radical 3, and the hypotenuse to be 2. Well, you should recognize that as a 60-degree reference angle, or a pi over 3. So that means here that the theta, this theta right here, okay, which would be what? That theta would actually be then negative pi over 3. Okay. All right, let's do one more of these types of problems. 19. tan inverse of 0. Tan inverse of 0. All right, well, this is a little different, right? Because the ratio is 0. It's not positive or negative. And that, again, as you guys get used to this, that's going to jump out at you immediately. Well, let's again be reminded where we are compelled to look for our inverse tan angles. Okay, so we're only allowed to look between negative pi over 2 and pi over 2. Okay. Well, think about it. Down here in the fourth quadrant, you're negative. Okay. Here tan is less than 0. Here tan is greater than 0. So, yeah, tan is 0 right here, right? Remember, tan is y over x, and if you choose, you know, the point 1, 0 here, y over x is 0. Tan is 0 here on the x-axis. So, what angle is that? It's 0. That's the angle measure right there. It's 0. Okay? Tan inverse of 0 is 0. Yeah. Okay. Let's jump down to a couple of exercises from 23 through 40. These are calculator problems. So you'll have to get a calculator out. Yeah, I know I hate the calculator, so I got to go back to my desk here and get a calculator. Hang on. Okay. Hey, for these exercises, I'd like you to be in rads. Okay, you're going to get an angle value back out here. And I want you to be in rads, not in degrees, all right? So let's do 3 of these, and let's just talk about them, and I think you'll appreciate these. So let's do an arc cosine, an arc tan, and an arc sine one, all right? So 23. Okay, he wants you to evaluate an arc cosine ratio of 0.37, all right? Well, 0.37, right? Nice ratio. 37 out of 100, 37 over 100. Hey, that's cool. Yeah, sweet, cool. Well, guess what? Only God knows the angle whose cosine ratio is 0.37, the angle between 0 and pi. Okay, we don't know that angle, so we're going to have to use the calculator. But just to give you an idea of what we're looking for again, let's draw a picture of that. So we're looking for the angle, since this ratio is positive, right? 0.37 is positive. We're looking for an angle over here in the first quadrant between 0 and pi over 2 that has that cosine ratio. Well, if you were to try to draw a picture of that, 37 over 100, that's smaller than 1/2, right? So because 50 over 100 would be 1/2. So cosine of 1/2, that's 60 degrees, right? Pi over 3. So if I drew this, I'd want to make it maybe a little bit straighter, a little bit more erect than you would a pi over 3 guy. Okay, like that. So this would be our 37, and this would be our 100. So think about it. Just think about it. The 100. If the 37 were 50 and you had 50 over 100, that'd be 1 over 2, right? Well, in order to make this 37 side smaller in ratio than 1 to 2, you're going to have to raise the angle. All right. So we know this angle is going to be bigger than 60. 60 is a pi over 3. Okay. You don't really have. Obviously you don't have to do all this. I just want to give you a feel for what you're looking for here. So the 61 would be more like this. Right? There's our tall bow tie. Okay, this would be pi over 3. So pi over 3, what is that equal to? That's equal to 1 point something, right? 3.14 divided by 3 is just slightly over 1. Well, this ratio here is going to be a little bit bigger than that. Hey, remember our decimal versions of these numbers? Half of pi is 1.57. Remember that? Okay, so what do you think arc cosine of 0.37 is going to be? Something between 1 and 1.57, right? This is a little bit bigger than 1, slightly, the pi over 3. Oh. Well, let's see, what is that? 3.1 divided by 3, 1, 3, 11 divided by 8. Okay, I'll cheat. I'll use the calculator here. Let's see. So pi divided by 3. So 1.0. Yeah, that's what I was going to say. 1.0 something. 1.05. I'm cheating looking at the calculator. All right, so our angle is somewhere between 1.0 and 1.57. So you want to take a guess there? Let's say it is roughly 1.28. All right, this is my guess. Roughly 1.28. They always like 4 decimal places here. 1.28. I don't know. We're just making it up now. 1. All right, that's my guess. All right, Boach's guess from the picture. Okay, all right. So now on your calculator, first thing, make sure you're in rads. Okay, so calculator. Okay, so be in rads first. So go to mode here. Okay, so mode, rad. Okay, so I'll check my mode here. It's in degrees, so I'm going to go rad. And if you've got the 84 graphing calculator, then you're just going to type it the way it's read here. So they don't write it as arc cosine in the calculator. What you need to do is do second function. You're going to do second function or second cosine, right? That's going to give you. That's going to be equal to cosine inverse. All right. This is the button this is the function you want to get out. So then you're going to type in 0.37. Right, so 0.37, and you're going to get out what? What do you get out? Let's check it out. Inverse cosine 0.37 is 1.19. All right, so my guess wasn't horrible. 1.191718. So 1.19, 1.1918. Okay, so again, our guess was not horribly off. Right, 1.28. I mean, we were off by roughly a hundredth. So that's not a bad guess. Just to draw a picture and come up with a decent guess. Okay. All right. I'm not going to do that every time. I know that's going to bore the crap out of you. Just bear with me though. But it's important that you can draw pictures and understand what it is you're looking for. That's important. All right. So let's do a couple more of those. How about 35 and 39? How about these two? 35 arc sine of 7/8. Well, again, I know you're right now just rushing to the calculator and you want to punch it out and get an answer. Okay, fine, I understand that. But again, it's important to understand what you're looking for here. You're looking for an angle whose sine ratio is 7/8, but you're only allowed to look for that angle between negative pi over 2 and pi over 2. Well, again, since the ratio is positive, right? The ratio is positive. The only place that you're going to the only place you need to look between these two quadrants is this, the first quadrant. That's where the sine ratio is positive, right? And remember, sine is what? It's y over r. So you would want to make the y side tall and the r side just slightly taller there, okay? So in this case here, we're looking at an angle, you know, go back to this slide here. We're looking at an angle steeper than the one here, the 0.37 cosine ratio angle, which generated this 1.19. So I don't know, what would you say there? Remember that pi over 2 is 1.57 in rad values. So I don't know, maybe 1.35. That's going to be my guess. My guess, Boch's guess. All right, 1.35, and these, you know, 2, 1. I'm just guessing there. That's stupid. That, you know, there's no way I could guess the 10,000th place. All right. I'm glad that God knows that. There's no way I know that. All right, so this is, again, Boch's guess. Okay, I know you already know the answer. I know that most of you have rushed to the calculator and already punched out the answer. I know that. But I like to think about this stuff. So there's my guess. So now go to the calculator. And, you know, make sure your modes and rads already. You're going to do second function sine, and then punch in that number 7 divided by 8, 7/8. And what do you get? How close was Boch on his guess? Second sine, 7 divided by 8. 1.06. 1.06. Well, see, look at this. That's actually less than I thought it looked like it might have been 7/8 ratio would have been bigger than than this angle here, this 1.19 angle, but it's actually smaller. Okay, so see, my intuition over this 7 to 8 relationship right there was bad. It was wrong. So it's actually less than the 1 point than that last angle. So 1.0654. 1.0654. Okay. Hey, you know, you learn stuff, right? Okay, so boom. My guess was not very good on that one. Okay, then finally, let's do one more of those. 39. Yeah, I should try to draw it more accurately. 7 to 8 seems steeper than that last angle, but it wasn't. If I had thought about it, I probably would have corrected that false assumption, but I didn't. Okay, how about this one? Okay, I know some of you are freaking out at the radical 372, and you think, oh, dude, that's a huge number. Well, all right, let's think about it. I don't think it's going to be that bad. So, first of all, remember where you look at, well, again, this is a calculator problem. So I know some of you are already done. You've already punched out in the calculator. I understand that. But again, think about what they're asking us to do here. To find the angle between negative pi over 2 and pi over 2 that gives that tan ratio, negative radical 372 to 1, right? Well, okay, so the quadrant I'm going to be looking in, well, you're not actually looking at it, you're just going to punch this out, but the quadrant that this angle would land in is down here in the fourth quadrant, right? This is where tan is negative. Now, if you were to draw this halfway descent, remember, this is a y to x ratio, okay? Radical 372, I mean, what is that? Radical 400 is 20. What's 19 squared? 100, 90 is 280, and 81, 361. So this is a little bit bigger than 19. So it's roughly equal to, 19 to 1, okay, ish. Okay, so that means the y side to the x side is 19 to 1. It's going to be pretty steep again. You know, if you could draw it accurately, it's probably going to be steeper than that. Let's see. Okay, so what you're trying to do here is you're trying to draw. This is my right triangle. I know it doesn't look really good, but so you know, negative 19 to 1 ish, right? Not too bad, but probably a little steeper than that. So it's going to be really super close, right, to negative pi over 2, which is negative 1.57. Okay, so what do you want to guess here? You know, what do you want to guess that this angle is here? What do you want to guess this guy to be? Okay, let's do a Boch guess on this. Oh, boy, so 1.45. Okay, we're going for negative 1.45. That's going to be my guess. 4562. Okay. It's good that I'm not addicted to gambling, because I would find some bookie that would give me odds on guessing these, and then I start betting and lose all my money, all that I have, which isn't a lot. But anyway, okay, so there's my guess, negative 1.4562. Boch's guess. Okay, think about again how we got that. We drew a we drew a terminal ray, right? There's the terminal ray, right? And then we dropped the perpendicular, and we try to draw it proportionate. You know, we try to draw it accurate to give us roughly this 19 to 1 ratio. So, you know, in other words, this unit here, this horizontal 1, if I counted those out, 1, 2, you know, it should be close. It's probably a little steeper than that. So we'll go negative 1.4562. Yeah, I don't know. Now I'm looking at it thinking maybe I want it bigger than that. 1.4. Okay, and we're going to go 1.4. I'm going to go here 1.48. Hey, I'm betting here, right? I'm betting. Okay, all right. So do the whole inverse tan thing. So second calculator. Second tan. Right, that's going to give you inverse tan. Negative radical 372, and that, drum roll please, second tan, negative radical 372. Whoa, negative 1.5. You know, I wanted to go steeper there. Negative 1.48. Okay, hey, you know what? You learn, right? Negative, okay, but I'm not too far off. I'm glad I went up, because I knew it was kind of steeper than the picture I drew. But it's so hard to draw a steeper picture that I was inclined just not even try to draw it right, which is stupid if you think about it. Negative 1.5190, rounded to 4 places. But again, consider my guess here. It's not too bad. All right, not a bad guess. Not a bad guess. I'm only writing that because you're not here. Okay, this is the answer. All right. Okay. That brings us to the last exercises, 43, 44, 47. Let's do a couple of these. How about 45 and 47? He wants you to use an inverse trig function to write theta as a function of x. All right. So this is the picture we get in 45. Okay, so what you might want to do here first, it's difficult to think backwards. It is, it's just very difficult. So you might want to think forwards first. So if you'll notice here, what is given in this triangle, all right, with respect to this acute angle theta here, is the y side, right, and the r side with respect to theta. So the ratio to go with here is sine, right? So the sine of this theta is y over r, right? Which means what? Which means that theta is the arc sine, or sine inverse, I don't care which one you use there, of this ratio. Okay, that's an important expression. You're going to see more expressions like that later, but that's all he wants there. And let's do one more of those. 47, we'll call it we'll call it a lesson here. 47. Okay, so again, look at what's given to you there in relation to theta. All right, you're given the x of the adjacent side and the r. So the ratio that you would want to use here, the easiest ratio to use certainly would be cosine, right? Cosine of theta. The cosine of this theta is equal to the adjacent side, the x side, to the r side. Okay, which means what? It means that theta is arc cosine, or inverse cosine, of that ratio. Yeah, my obsession with the colors, sorry. Okay, well, while we're at it here, let's go back and let's put in 43, because that's going to give you a tan one, an arc tan one. So we'll finish up with this one. So Dr. Larson gives you this triangle. Well, okay, hopefully what jumps out at you here is that the tan ratio is the ratio that you're looking at with respect to theta. Which means what, sweet people? It means that theta is arctan of x over 4. And that is the end of the lesson. And the kids, it's Thursday morning, and of course we're doing block day right now, and so first period is going to be done here in literally 45 seconds, which means the third period kids are going to be rushing in here and making all kinds of noise, so I need to stop now. Hey, have a great weekend. Go through this lesson. Hey, show your parents what we're doing, okay? They might get a kick out of this. And hopefully this will help you get through the exercises, all right? Homework will be on RenWeb. All right, I'll probably also send it in a note, all right? Take care. I will see you on Monday. There's the bell.